So the theorem that we had last day was saying that DFAs and NFAs are essentially the same from a computational perspective. So anything that you can compute with the DFA or model the computation with the DFA, you can construct an NFA to do the same thing. Vice versa, you can take an NFA and you can construct an equivalent DFA. So whatever computation you can do with an NFA, you can also do with a DFA. So although the NFA seem to have less states in some scenarios, although it seemed to be more efficient, if you like, although efficient is a dangerous word in this course, because next semester you will be looking at what is efficient or was complex, but certainly it seemed to be a more compact version of a DFA. But from a computational standpoint, the type of problems that an NFA can model are no different than what a DFA can model. So they're exactly the same. We're going to introduce today, essentially for something that we're doing today and on Thursday, a new type of NFA, and what we call an Epsilon NFA. Now this is just a special type of NFA, so sometimes I will only just refer to DFAs and NFAs, but within the NFAs we will also be considering these Epsilon NFAs. Essentially Epsilon NFAs, some people described it as a free pass when you see this Epsilon. It's quite a good way to do it, because sometimes you don't always get input into a system for it to change its behavior. So for instance, where we had the front doors of the CSB, you got information coming from outside, information from people entering or exiting from inside, but fundamentally the doors also closed when there was no input whatsoever. And it's how do you actually represent that reset function. So that's a nice way to think of this, is almost like a reset in this case. How do you reset the door's behavior when there's not actually an input to drive that change of behavior? And what we're looking at, previously we represented by an alternative input called no input, but what we can actually do is denote it with this small character epsilon. So all we're simply saying there is that if our input at the closed position comes from the front pad or the rear pad, we will change behavior to open. There's an option then, without taking any further input, for us to move back to a closed position without receiving any further input, or if you wish, you can just go back into that closed position. Again, you restart over again. So that's all it simply does. It allows you to transition between states without actually having a specific input into the system. Now this new special character epsilon changes things for the definition of an NFA, just slightly. In general it stays the same, but now we will have a 5-tuple where the alphabet will now get changed to this sigma epsilon. And all that is represented is whatever the alphabet was before, union with epsilon itself. It's just another character is now added in. So it means the transition function, instead of going and taking a state and one of the alphabet symbols, it will take a state and the alphabet symbols plus epsilon as an input and get you to another state or set of states for the output. If you are reading around this topic, as mentioned, there's a number of different ways to do it. Sometimes this is denoted by sigma star is one possible notation, and we'll see actually what this star means later on. But fundamentally there's a number of different ways. Now another theorem that we come to is that these epsilon NFAs are just special forms of NFAs, and as such, for every epsilon NFA there exists an NFA to do the exact same thing. And for every NFA, of course, we know that there's an equivalent DFA. So all three are equivalent, and the epsilon NFAs we just say are a special type of NFA. So I'll generally only refer to NFA and DFAs, but I'm introducing these epsilon NFAs because they'll become quite important in the next chapter. And part of the confusion that arose on Friday's tutorial was how you transition between these epsilon NFAs to create an equivalent NFA or DFA. So if you go out reading some supplementary resources, you may see things called epsilon closure. Epsilon closure of a state is essentially a way to transfer between an epsilon NFA to an NFA, getting rid of the epsilon component. What we're going to do is we're going to move between an epsilon NFA to a DFA. So to try to illustrate this, we have three equivalent things that are DFAs, that they're exact same as NFAs, and then these new epsilon NFAs. And by our theorem, which we're not going into the detailed proof, but these are all equivalent. Now what typically happens is to get from an epsilon NFA to a DFA, most people will go first into an NFA and then go into a DFA. What we're going to be doing now to show the equivalence of the epsilon NFA, we're actually going to show that you can translate this epsilon NFA into a DFA in one go. And because you can translate it into a DFA, you can automatically translate it into an NFA, as we found it before, and the whole order is kind of cyclic. Now what we find is to transfer DFA into an epsilon NFA, it's quite simple. You don't actually need to add in any special transitions, you just need to, similar to defining a NFA from a DFA, you just need to change the transition diagram. So an epsilon NFA may have epsilons in it, may not, but generally it will have. So if you read a lot of textbooks and you see things called the epsilon closure of a particular state, that is likely to be taking this direction around and be going from an epsilon NFA to an NFA and all the way around. What we're going to be doing is essentially the exact same thing, but we're going to be going straight to a DFA. That's what we're going to be doing. So to have a look at an example, here we have one particular epsilon NFA. So you'll notice it does just look like any other NFA in the sense that we do have a ambiguous transition in Q2. A can go to Q2 or it can go to Q3, and in Q3 there's no real knowledge of what to do with a B or a C. The transition diagram, which is slightly changed from one that was in the previous notes, looks relatively similar as if epsilon was any other input. If I'm in Q1 and I get an A, well, there's no defined transition for what to do at Q1. And that differs depending on what type of textbook you might be reading, but for our purpose we're now going to stick to this consistency. So there's no transition for A apparently at Q1. If I get B, I can go to Q2, and if I get epsilon, if you like, as just another input character, I could move to Q3, and that's where I finish. If I'm in Q2 and I get an A, I've got the option to staying in Q2 or moving into Q3. And if I get a B, I move into Q3, and there's no apparent transitions defined for epsilon for Q3. Or for Q2, sorry. For Q3 then, there's a transition from Q3 to Q1 by A, and there's no apparent transition for B or for epsilon in that case. So that how people define these transition diagrams can change depending on the textbook, but we're now going to take this format. So we want to convert to, in fact, a DFA. Let's have a look at what we would do. So if we just recall that transition table, the translation from an epsilon NFA to DFA is going to be quite similar to what we would see in the case of a NFA to DFA. So this was Q1. We had a transition, an epsilon transition to Q3. Transition back with A. Okay, so we have this is our automata, which we're hopefully going to translate into a DFA. If we take a couple of words to begin with, let's take some words like AB. If we were to translate or to trace the path of what happens to AB, well, if we're at Q1 and we get an A, one option is that we just end up in a dead state because there's no apparent translation or transition from Q1. So that is one option. Another option is if we're at Q1 without actually reading from our input, we can use epsilon to jump to Q3 as a free pass, as some people have described. We can get to Q3. Then at Q3 we can read the A, which will get us back to Q1. So we could use epsilon to get to Q3, and then we could read an A to get back to Q1, and then if we read a B, we'll get to Q2. What if we had the string A, B, B, A? That's another possible string. So again, at Q1 we could try to read an A and actually end up in dead state, or we could use epsilon to get to Q3, then read the A to get to Q1, then read B to get to Q2. So I've just gone Q1, epsilon to Q3, A takes us back to Q1, the B takes us to Q2, the B takes us to Q3 then, and then finally an A would take us back to Q1, and we would accept this word in this case. So the epsilon is essentially allows you to transition along that path, even though it's not there in the input, it's an empty input, it's nothing. So you can transition between two states without actually reading from your input string. What we're going to do is keep that in mind when we actually define our DFA. So again, trying to keep consistent. I also want to change some solutions on the last tutorial because when converting between NFA and DFA, again, I think I mentioned lastly, there's a number of different ways you can do it. We're prescribing, if you like, in this course, that we start with the original start state. There are other methods which can often get you a more simpler solution, which start with the first non-empty state, but that's only an option, and it gets a bit messy at other times. There's other methods that actually take all possible states in the NFA as options, and they work from that. But we'll try to keep consistent with the original start state. If I'm at Q1 and I have the string A to read, well, I could end up in a dead state. Another option would be that I would take Epsilon to Q3 and then read the A, and I would finish at Q1. That would be a valid way to read the string A. So, in fact, we could end up back at Q1 if we had an A. That state's already in our list, so we won't add it in. If we get a B in Q1, we'll move to Q2. That state is not in our list, so we'll add it in here. We could have at Q1 decided take an epsilon to Q3 and then try to read a B, but that would end up in a dead state, so we don't add it into our list. So you could have taken an epsilon transition to Q3, but for the case of reading a B, it has no benefit. It adds nothing, no new states to our transition diagram. If I'm in Q2 and I get an A, I can stay in Q2 or go to Q3. And we'll add that into our list. If I'm in Q2 and I get a B, I have to go to Q3, and that's new, so we'll add that into our list. If I'm in Q2 and I get an A, I would stay in Q2, and I would potentially move into Q3. And if I'm in Q3 and I get an A, I would go back to Q1. So we'll add that into our list. And also, if I'm in Q3 and I get an A, I could move to Q1 and then use the epsilon transition to move back to Q3 as my finishing point. Now Q3 is already listed here, so we won't add it in, but that would have been fine to do. So we can either use that epsilon transition after reading the string, or in the initial case when we started Q1, we used it before reading our string. So Q3, if we get an A, we can read the A and finish Q1, or we could read the A and then use epsilon to get back, and we would finish at Q3. But Q3 is already listed here, so we don't have to add it in. This is a new state, so we add it into the bottom. If we're in Q2 and we get a B, we go to Q3. And if we are in Q3 and we get a B, then we'll go to dead state, so we don't add anything in. Q3 is already listed, so we don't have to add it to our states. If we're in Q3 and we get an A, then we can go to Q1 and stop there. Or we can go to Q1 and then take epsilon back to Q3. So we would get Q1, Q3. If I have a B in Q3, I would end up in a dead state. There's no options there. And these are two new states, so we have to add them in. I'm in Q1, well, essentially, if I'm in all possible states, if I'm in Q1 and I get an A, I could end up in Q1. If I'm in Q2 and I get an A, it's Q2 or Q3. If I'm in Q3, it's Q3 and Q1. So Q1 and then use epsilon back to Q3. So essentially it's all the states again. If I have a B in Q1, then I can go to Q2. If I'm in Q2 and I have a B, I will go to Q3. And if I'm in Q3 and I get B, I go to a dead state, so I don't add anything else in. If I'm in Q1 and I get an A, well, I could go to dead state, or I could use epsilon to go to Q3 and then read the A, which will lead me back to Q1. If I'm in Q3 and I get an A, I will go to Q1 and finish, or I'll go to Q1 and then use epsilon to get back, which will make me finish at Q3. If I'm in Q1 and I get a B, I go to Q2. And if I'm in Q3 and I get a B, I will go to a dead state, so we don't add anything else in. And if I'm in a dead state, remember that means the system will never get back to accept. So we always want to remain in a dead state, no matter what the input actually is. Does anybody have any questions there, or any comments? Any questions? Not too sure where some of the transitions came from, or maybe what some of the transitions are. Okay. So as before, we can, if you like, rename all of these states. So for instance, Q1 could be S1, Q2 could be S2, this new state could be S3, S4, S5, S6, S7, if you wish. I'm not going to do that. I'm just going to keep them as they are. So we have Q1. If I get an A, I'll stay in Q1. And if I get a B, I'll go to Q2. If I'm in Q2 and I get an A, I'll go to this new Q2, Q3. If I'm in Q2 and I get a B, I'll go to Q3. If I'm in Q2, Q3 and I get an A, I'm going to go to Q1, 2 and 3. If I get a B in this state, then I'm going to move to Q3. In Q3 then, if I get an A, I'm going to go to another new state, which is Q1, Q3. If I get a B in Q3, I'm going to go to a dead state. I'm in Q1, 2, 3, and I get an A, I'm going to stay there. If I'm in Q1, 2, 3, and I get a B, I'm going to go to Q2, Q3. Q1, Q3, if I get an A, I'm going to stay there. And if I get a B, I'm going to go to Q2. If I'm in dead state, doesn't matter if I get an A or B, I want to stay in a dead state. There we go. So is our automata complete, this new DFA? So hands up if we think yes or no. So hands up for yes, we think the automata is complete. And hands up for no, there's something missing. Okay. Hopefully we'll think. So what's missing in this automata? Accept states. So in the original Epsilon NFA, Q1 was an accept state. So anywhere that we see Q1, it's also going to have to be an accept state. So we have an accept state here. We have an accept state here. And we have an accept state here. This is probably rough, and then if you were to present this in, say, an assignment, you would maybe redo this out nicely once you've had another go at looking at the order. And there's one other thing missing. What do we think it is? Start state. And which start state do you think we should choose? Given that's the previous Epsilon NFA.
Q1.
Q1? Yeah. That would be an absolutely fine start state to use. What you will find is if you go to SIPSR textbook, this same example is carried out. It's slightly different the way it's conducted, and indeed they get a very different answer for how it's conducted. They use a very different start state than Q1. So in the supplementary resources, actually, I think, direct you to the pages where this is. On the top of my head, I think it's maybe section 138, possibly 138. If you have a look, it's very different, actually. That there are options for other possible start states that would lead you to the same result. So that is converting from an Epsilon NFA to a DFA, and we have accounted for all possible paths that our Epsilon transitions could have got us. Do you have any questions on either Epsilon NFAs or NFAs or DFAs before we move on? Okay. Now the behavior of all these automata is very much dependent on what is the accepted output of the automata. That's really fundamentally what it's interested in. And previously we've commented that there's the language of the automata, that is any possible strings that are accepted by the automata. We're going to be looking at a very special type of language. So language, just remember, is all corresponding subset of strings over a certain alphabet. The language of an automata is then the subset of strings over a certain alphabet that the automata will accept. We're going to be focusing in on this topic on a very special type of languages, and those are regular languages. Regular languages are simply any language that is accepted by an NFA or DFA, and for that matter then an Epsilon NFA. So if you can represent, say, a language by an automata that we've covered so far, it is regular for definite. So to give you some example of some languages, so example of some languages, we could have the language of all strings over the alphabet A, B, C, which are in alphabetical order. So that is the set of strings, might be A, B, C, that's a string which is in alphabetical order. B is a string in alphabetical order, C is a string in alphabetical order. AA, AB, AC, BB, BC, and so on and so forth. So infinitely many strings, and they're all in alphabetical order. Can we define an automata that would recognize these strings? Could be an NFA, could be a DFA, an epsilon NFA. And the answer is certainly yes. We could have something like this. This automata, you could have constructed a DFA. And do, if you wish to put into practice converting epsilon NFAs to DFAs, try converting this to DFA. Design a DFA from scratch and see if you can convert it. But essentially, if we start at Q0, we could have A's at the beginning, and then we have the option to move to Q1 with epsilon without taking any input characters, then take some B's, and then use epsilon, and then take some C's if we wish. And we would finally accept. So if we take the string A, do we accept the string A? Well, in Q0, we get an A. We could read it, and are we okay? Any questions? If we're in Q0 and we get an A, we could come back to Q0, then use epsilon to move to Q1 and epsilon to move to Q2, and we finish in an accept state. For the string B in the language, if we're in Q0, we could use epsilon to move to Q1, read the B, and then move to Q3 or Q2, sorry, with epsilon again, and we finish in an accept state. If we have C, we start in Q0, we can use epsilon to move to Q1, epsilon to move to Q2, then read the C, and we'll finish in an accept state. If you try a word like BA, which is not in the language, this automata should reject it. So if we have BA, well, firstly, we could end up in a dead state because we don't know what to do with the B here. Another path would be at Q0 moving to Q1 with epsilon, then reading the B, and then we're stuck because we need to read an A, and we don't have a transition either here for A or indeed in the future for A. So once we seem to pass the option of using our A's or option of using our B's, then we can no longer go back and read words or letters that came before, and that's why it's in alphabetical order. Another possible language would be all binary strings, like the language of all binary strings, that is over the alphabet, zero, 1, that end with a 1. So in that case, we could have, well, the string 1, 0, 1, 0, 0, 1, 1, 0, 1, and then so on and so forth. Can we construct an NFA, DFA, or epsilon NFA to recognize all of those strings, and indeed reject all strings that wouldn't be in that language? Does anyone want to have a go at that? What do you think we could do? Maybe someone over this side of the room. Design the DFA, NFA, or the Epsilon NFA. What's the thing we want to do? We want to make sure we're greedy. What do we really care about? That it finishes in 1. So what would I do if I'm Q0 and I get a 1? Would I stay in the same state, or would I move to a different state? Stay there. Good. What if I get a 0? Any thoughts? We could stay there as well. So now we're going to essentially keep in that loop for as long as we have 1s and 0s, but how are we going to get to an accept state? Okay, if we did that, then what if I had 1, 0? I could go 1, 0, and then epsilon and potentially get to an accept state without having finished with a 1 at the end. So the crux is to get to the accept state, I want to make sure that the last character is a 1. Just a 1. And any further characters would lead me to a dead state after that. Let's call it QX and QY. So these are 2 regular languages. Now what we're going to be looking at is a couple of operators that are covered in regular languages. We've seen operators before in sets, and these are going to be quite similar operators. So this is in the notes, but we'll cover it, if you like, slightly quicker in this case. So if we call the language of all strings over the alphabet or alphabetical order A, we'll call that language A, and we'll call the language of all binary strings that end with a 1 B. That's language B. What we're going to define is the union of 2 languages. Is denoted A union B and consists of all strings that belong to A or belong to B. So we could have strings like A, B, C from before, AA, AB, and so on and so forth. And we can also add into this set then the string 1, 0, 1, 0, 0, 1, 1, 0, 1, and all the remaining ones in that case. So just like the union of 2 sets, the union of 2 languages is just taking all the strings from one language, all the strings from the other language, and combining them. And as it's a set with no repeats. So that is simply the union of 2 languages. The next operator we're going to be looking at is the concatenation. Two languages. And this is denoted A circle B and consists of strings whose first component comes from the language A, and whose second component comes from the language B. So example of some of those strings, given what A and B are, given we had the language of all alphabetical strings over all strings over the alphabet A, B, C in alphabetical order, and we had all those binary strings ending in 1. Could somebody give me one particular string that belongs to A concatenated with B? Take something from A and add on to it then an element from B. A1. So the first component comes from A, the second component comes from B. We could have A01, A001, and so on and so forth, or we could have B1, B01, and so on. We could have somewhere AA001, that would be another element in our set, or indeed in this language. The last operator then we're going to be looking at is the star operator. Applied to a given language A, that's denoted A star, is any possible repetitions of elements from A. And when I say any possible repetitions, that also includes no repetitions. So if we take the language A star, that will be equal to potentially epsilon at the empty string. So no repetitions of the words from A. We could have A, we could have AB, we could have AA, BA, and that starts to look slightly strange. But essentially we've taken something from A and another thing from A and another thing from A and another thing of A. So although this is not in alphabetical order now, you then don't have a possibility of this new language may not necessarily be the same as the previous language. So though we prescribe alphabetical ordering in language A, now we just have to concatenate various elements of A together to give us another new element. We could also get that element by taking the element AA, concatenating a B, and then concatenating an A. So there's more ways to get to the same element. But fundamentally, it is all those elements of A, followed by another element of A, followed by another element of A, and so on and so forth, including potentially no repetitions of A. Now the one last thing I want to do just before we leave, I want to give you an idea of what we're doing next day, which is the closure of the union, concatenation, and star on regular languages. Now I'm introducing this because you have a bit of homework to do, unfortunately, for Thursday. So to say something is closed over a particular operator, it means that if I apply the operator, I still end up in the same context that I began with. So I'll give you an example. Natural numbers are closed under the operations of multiplication and addition. Natural numbers are not closed under the operations of division and subtraction. To explain that, if I take any two natural numbers and multiply them, I will always get back to a natural number. If I take any two natural numbers and I add them, I will always get back to a natural number. If I take two natural numbers and subtract them, I may not necessarily get to a natural number. For instance, I could take 1 and subtract 2, and I get -1, which is not a natural number. I could take 2 and divide it by 3, and that gets us 0.666 and so on and so forth. That is not a natural number. So the natural numbers are not closed under the operations of division and subtraction because you do not end up with a natural number. What we're going to be showing next day is that the closure of union concatenation star for any regular language gives you back another regular language. Now the formal proof of this is online in a video that I've done out, and it's available on Canvas. So what I want you to do in ahead of next week or Thursday's lecture is to watch that short video. It's about 15 minutes explaining why the union concatenation and star operators are closed over regular languages. And we'll be going through some examples of them on Thursday.